20 minutes.
Okay. Good evening. My name is Yuriy, and now I will present my scientific work, structural investigation of bovine insulin by two-dimensional NMR spectroscopy. My scientific supervisors are Professor Vladimir Klachkov and senior researcher Sergey Efimov. First of all, creation of new effective drugs is one of the main questions now. And to carry out the task, it's essential to understand the mechanism of interaction of the drug with various ligands and cell membrane. The first step to understand this mechanism is structural investigation. The methods for structural investigation are developing nowadays, but most useful are X-ray diffraction and NMR spectroscopy. But only by NMR spectroscopy we can obtain a structure of protein in water solution, but which is close to physiological membrane. So, as the object of my research was chosen a bovine insulin. Insulins play an important role in biochemical processes because its binding with receptor provides a mechanism for glucose production. However, many people suffer diabetes, and which characterized by reduced or completely absent production of endogenous insulin. The structure of human insulin is known from 1969. But the solution structure of bovine insulin were unknown until today. We not found the articles about this. And for liquidation structure, the bovine insulin was dissolved in water solution in pH 2.86. So in the picture you can see the amino acid sequence of bovine insulin consists of two chains. The short is called A chain, and the long is called B chain. And you can see three disulfide bonds. So, the aim of my research is to assign NMR signals of bovine insulin in solution by two-dimensional NMR spectroscopy and to simulate its structure. The sample was purchased from Sigma Aldrich. Spectra were recorded on Brook spectrometer at proton channel frequency 700 MHz, where temperature of the sample was 20 and 35 degrees. So, what information we can obtain from high-resolution NMR spectra? First of all, from nuclear Hauser effect experiment, we can determine the distance between the protons about such ways. Secondly, we can determine torsion angles in molecule by using spin-spin interaction. And thirdly, from amide exchange data, we can obtain data about the terminals of protein, and we can predict a location of hydrogen bonds. However, I previously said we must use two-dimensional methods. They consist of two or more radio frequency impulses and 4 periods between them. The first period is preparation, in which spins are going to thermodynamic equilibrium. After the first impulse, spins are processed at very frequency, and during the mixing period, the magnetization is transferred from one spin to another, and we can detect this by free inductional decay. And the intensity of recorded signal will be equal to formula is presented, whereas eta represents the efficiency of magnetization transfer. So we used these two-dimensional methods. First of all, we used a TOXI method, which yields through bond correlation via spin-spin coupling. Additionally, we used a noisy spectrum, which yields through non-bond correlation via dipole-dipole coupling. So, in picture you can see an overlay of spectrums. The axis is a frequency in ppm. So, for example, choose 5.5 ppm on the vertical axis. We can see four blue signals. It indicates that we see signals between phi residues, and we can predict a protein folding, such as alpha helix. Additionally, we recorded a heteronuclear spectra, such as HSQC. HSQC yields through directly bonded proton to heteronuclei, such as carbon. So we completely signed the spectra, and using by heteronuclear homonuclear spectra, we completely access the spectra assignment. So, for our analysis of noise signals, we built such a diagram for A chain and B chain, respectively. This diagram shows the presence of signal in the noisy spectra. For example, for first line, it shows presence of signal between alpha proton and amine proton, between neighboring residues. And so, if we see a long-range distance signal, we can predict a second structure formation, such as helix. So we clearly see this formation from 2 to 5 residue in A chain, from 12 to 18 residue, and we can see a long helix in B chain. Additionally, we see a strange signal, which we must check. So, it's well known that chemical shift indexes provide information about second structure formation too. If a chemical shift index indicates the deviation between experimental chemical shift of nuclei, such as carbon, and minus random coil chemical shift. Values of random coil chemical shift was taken from Wishart article. If a deviation is positive and goes through 3 or more residues, we can predict a helix formation. So it's clearly seen we can predict a helix formation in the beginning of A chain, and we see a long helix in B chain. Additionally, if deviation is negative and goes through 3 or more residues too, we can predict a beta sheet formation. But in presence, in case of insulin, it may indicate an oligomerization of insulin. It's what written in some articles. And to check this, we must detect a diffusion coefficient dependence on concentration. So the next step was simulation of structure. We used a molecular dynamics method. In Explorer program, molecular dynamics simulation involves solution of Newton equations of motion for a system of n-interacting atoms. So in the beginning, we have a disordered structure. By using the experimental restraints and by including some potentials, finally we obtain a structure with minimal energy. So it mainly consists of 4 steps. We starting process of dynamics, then we calculate a profile of energy, which is quite complicated, have many local minimums and one global minimum. And to find the global minimum, many experiments consist, but we used a simulation analytic method, which are most useful for proteins. And finally, we obtain a correct structure by using some refinement procedures. So we do this, and we obtain a couple of structure of insulin. But in the slide, you can see the structure with minimal energy. You clearly see there are 3 helices, which was predicted by another parameters, and it's quite good for me. Additionally, we checked the quality of obtained structure. Quality was controlled by using a Ramachandran plot drawing. Ramachandran plot shows the energetically allowed regions for dihedral angles in molecules. So you can see that there is one residue lies in the allowed zone and others are lying in the most favored zone. Additionally, we evaluated a root mean square deviation for 3 best structures, and it's clearly seen its mean value is equal to 3 angstroms. So these facts proved the good quality of our structure. And finally, to check the oligomerization of bovine insulin, firstly we registered the dosage spectrum, which and evaluated the diffusion coefficient with, and by using these formulas of Stokes-Einstein equation with this coefficient, we evaluated a size of protein because its surface was like an ellipsoid, and its value was quite bigger for a monomer. And to check this, we registered the number of specters with different concentration of protein in solution. And If the diffusion coefficient didn't depend on concentration, it must indicate a monomeric form in solution. But if diffusion coefficient fills the protein concentration, it can fill, we can say about a oligomerization. So it's clearly seen that diffusion coefficient is not constant, and we can predict oligomerization of bovine insulin. So finally, summary is presented. So complete assignment was done. In my spectra we see cross peaks not only between the protons, but also between the amide protons and protons separated by 1 and 2 amino acids. A simulated structure completely satisfies the experimental data, and such way of protein concentration dependence of mobility proved dynamical insulin oligomerization. Thank you for your attention.
Thank you. Please, questions? Maybe. Please, sir.
I have two questions. The first one is the secondary structure that you show us on the 10th slide consistent with the secondary structure elements in your model, three-dimensional model?
10 slides?
Yes. Yes. Is this secondary structure consistent with secondary structure in the model?
No, I think yes. We see at the beginning a helix in A chain. What is helix in the beginning of A chain and in the tail of A chain, and the long helix in B chain.
But I can't see any beta sheets on this model.
Beta sheets, it's formed only for if oligomerization.
Okay.
It's from articles every.
Okay, thank you. And my another question, in the 7th slide, we could see HSQC spectrum. Yes, on the spectrum we can see lots of unassigned peaks. Is it only noise, or it is not important peaks for us?
This?
Yes.
It's noise. Not quite good, I presented. It's toxic spectrum.
Oh,
it's
okay.
Quite noisy.
Thank you very much.
The second question, yeah? This is
Thank you. So there was a slide containing RMSD. Could we go to the slide, the RMSD? Could you explain RMSD with respect to what? Like, did we solve the structure as a bundle of structures like is usually done, and RMSD is basically like a thickness of a bundle, or is it RMSD relative to the structure of the human insulin, or what is the RMSD?
We obtain a couple of structure, and three best we aligned, and this is deviation in three best bovine structures.
So that's chosen three best structures and the RMSD in this bundle of the structures. I was wondering, like, how many NOEs per residue did you have?
I have 500 residue.
And that is per 40 residues in insulin, right? Something like that?
Not between alpha protons, beta, and is quite big.
I wonder also how it compares with the human structure. I think you implied that it's known, right? But didn't comment on it.
But in human we doesn't see oligomerization, and we see but we compare with crystallography structure of bovine insulin. It's quite differs from this, and for me it's a good result.
Okay. And the last also towards the end, you had this diffusion coefficient that's concentration dependent. Could it be sort of non-specific effect, because when you add a lot of protein, the solution simply becomes viscous? That's not so much really, the molecules are just rubbing shoulders. It's not really like a full-fledged aggregation.
No, it can be, I think, but firstly we reduce it on this concentration, and by adding water we dissolved. And temperature was constant, 20 degrees was.
Okay, thank you.
Excuse me, but what does it mean, relative protein concentration? What does it
Because
mean?
it's it was one height when we half and added water. Ну, то есть я имею в виду, что половину был целый столбик воды, мы половину убрали столбика и долили воды еще больше, то есть 2 раза разбавили, соответственно. То есть не измеряли, то есть качественно больше оценка.
Okay, I have a question, and I already have a mic. So I have 2 questions actually. First one about the diffusion coefficient. I work with proteins, and the protein diffusion coefficient, the values that you present probably correspond to the protein with molecular weight of at the limit of detection by NMR. I think that some lines should be broadened if you have the protein with such a diffusion coefficient, and I think that some inconsistency could be here because you observe nice spectra and observe such a diffusion coefficient. How can you comment on this? And the second question, if you have some oligomerization, probably you have not only one type of oligomers, for example 10 mers. It seems that you have some distribution of them, and if you have such a distribution, probably this could lead to different structures, and how this inhomogeneity in structure reflected in the quality of your structure and quality of obtained structure.
Yes, about the first question, how we can do this? We detected the noisy spectra in different mixing time for tyrosine ring signals. And from this dependence of correlation, we evaluated the correlation time, and then by formula we evaluated a diffusion coefficient. It's not from DOSI experiment. And about the second question, yes, I think very small forms can present in solution. It will be the next step of my investigation. We only stop on monomer solution, structure solution.
One more question? No. Thank you again.